The inverse of a linear transformation can be identified using this process. Once we have your definition of your linear transformation, take its standard matrix, then find out if the inverse of the said standard matrix is defined or is possible. Once it's not, automatically you can declare that the linear transformation is not invertible. But since if it has, multiply that with a certain vector signifying the composition of your domain, then you can decide the form of your inverse of a linear transformation T. So take note that we have here the transformation from R2 to R2, since we have two components here and two components for our codomain. In short, we are expecting here a 2 by 2 matrix. That's for your standard matrix here. The standard matrix is a 2 by 2 matrix where the first column are all the coefficients of your x, and the second column will be the coefficient of your y. Your first entry is 5x, so you will have 5 here, and since there's no y coefficient, that's 0. Next, 5y, there's no x coefficient, the coefficient of y is 5. This is the standard matrix of this given linear transformation. Let's see if the inverse is possible, or if this matrix is invertible by following this process. This is the process of determining the inverse of a 2 by 2 matrix we've learned in our previous discussions. So we are going to take this expression. So first, our A here is 5, B is 0, C is 0, D is 5 as well. So with this, we are going to solve first this denominator representing our determinant. If the determinant is 0, then this would be undefined, and hence our A is not invertible. Ultimately, our linear transformation T is also not invertible. Let's try. A is 5 times D, which is 5 minus 0 times 0. That's 25 minus 0. So our determinant is 25. Hence, our A here is invertible. Okay? And of course, our linear transformation of T is also invertible. Let's try to solve for the inverse. The inverse is 1 over, that's 25, your determinant earlier, times your D is 5. So negative of 0, negative of 0, and then 5. Of course, that's still 0 and 0. So your inverse is equal to 5 over 25, or 1/5. This is 0, that's 0. This is also 1/5. Okay, this is now the inverse of our standard matrix of the linear transformation T. This will be used to be paired with a certain vector V, which is the components, or has the components of x and y, to solve for the composition of our linear or the inverse of our linear transformation. So we have here our inverse is 1/5, 0 is 0 1/5 times x and y. So when you multiply that, 2 by 2, 2 by 1, you're expecting a result of 2 by 1 matrix. So this is 1/5 times x. So we have 1/5 x, 0 y, so this is just 1/5 x. Denominator, 0x, and then 1/5 of y. These are now the entries of your inverse of your linear transformation x, y. You'll have the first entry, 1/5 x, and then the second is 1/5 of y. This is again the inverse of this given linear transformation. Let's duplicate the process for the second. Again, let's solve for the standard matrix for this. So negative 2x and then 0y, 0 and then 2y. Let's find out if the inverse is possible. So you will have 1 over AD minus BC times D, A, negative B, and negative C here. So our A is negative 2, B is 0, Z is 0, D is 2. So AD minus BC, our determinant. Let's check if it's possible, if it's not 0. Negative 2 times 2, 0 minus 0. So you have negative 4 minus 0. Our determinant is negative 4. It's a non-zero value, hence our inverse exists in this form. 1 over negative 4. Okay? Times your D, which is 2, 0 or negative 0, negative 0, and then negative 2 here. In short, our inverse is, you have negative 2 fourths or negative 1 half. That's 0, 0, and positive 2 fourths or positive 1 half. This will be then multiplied to, again, a vector representing xy. Negative 1 half, 0, 0, 1 half times x and y. Having the form negative 1 half of x plus 0y, so it's just negative 1 half x, 0x, and then positive 1 half of y. So the inverse of a linear transformation t is equal to negative 1 half x and positive 1 half of y. It's invertible, and this is the inverse of the said transformation. We have this in our second answer here. So this is how we solve the inverse of a linear transformation with a 2 by 2, R2 to R2. Our next examples would be R3 to R3, so please bear with that because we will have to use a different method of solving the inverse because this method is only possible for 2 by 2 matrices. Thank you very much for watching.